It's my distinct pleasure and honor to introduce our next speaker, Professor Jacqueline Le Moigne, who joined us recently at the University of Miami. She's an amazing hire, an amazing individual who spent most of her career working on AI and many other applications to space science, earth science. She got her PhD at the Sorbonne in France, and then spent most of her career at NASA. This is where we met, I wouldn't tell you how many years ago, and worked at NASA for many years with a lot of accomplishments, published over 200 papers, had a lot of leadership positions at NASA, and her most recent position was program manager of ESTO, and she joined our university in October. And without further ado, Professor Le Moigne.
Thank you. Okay, thank you. So good afternoon. So today I am going to talk about AI, digital twin, and technology trends for smart city. So, so as Yelena said, at the end of my career, I was a program manager at NASA, and my program was focusing on technologies for earth science. So all the technologies that will be needed by earth science in the next 5 to 10 years. So at some point I became interested in smart cities and urban digital twins, and I asked Gardner, it was in 2021, I asked Gardner to perform a study to see what were the technologies that will be needed for smart cities, and in particular what were the technology gaps. So of course since 21, probably most of the technologies have moved to the right, which means that some of them matured, but we can see that, for example, artificial general intelligence is still not there, but there are things like foundation models or blockchains or distributed systems or digital twins that have become a little bit more mature. So as part of these technologies, I am going to focus on three main areas. One on artificial intelligence and data analytics, the second one on advanced computing with quantum and edge computing, and the third one on digital twins. So to start with AI and data analytics for smart cities, so I see these technologies being really divided into two different groups. There are the technologies on the left that are related to IoT and IoT sensor web and IoT infrastructure, and the one on the right are more for data analytics and analysis of large amounts of data. So on the left, for these technologies that are related to IoT and the sensor web of various sensors. The first one is situational awareness, trying to understand what each sensor is capable of independently and as a network. Being able to identify and discover these IoT sensors depending on the information that is needed, being able to process the data on the edge at each of these sensors, and being able to acquire data in a dynamic fashion, and finally being able to provide some security, some advanced communications of course, but also some security such as blockchains. On the right side, from a data analytics point of view, the first one is to be able to plan and schedule. So not only this IoT sensor, but also schedule the data acquisition, the data analytics, how to and then after that to take all of these various diverse data and do some information and data fusion. And finally, everything related to models. So being able to develop some fast models, some surrogate models, some emulators, being able also to take all various types of models and being able to interconnect them. So not only, so of course I was in the earth science field, but also in the smart city field. Do we want to connect the smart city models with other types of models like earth science or health or other information that can impact these smart cities? So this is a little bit the same type of information, but seeing from a different perspective. So this is the two main areas, the one that was on the left and on the right. But the first one, the technologies that will be needed for this type of AI will be the smart sensors, the planning and scheduling, the intelligent agents, being able to have some knowledge-based system, and some reasoning also, but for this IoT sensor. So for the technologies that were on the right that are now at the bottom, it's really everything related to data correlation and discovery and analytics. So in this case, the technologies are more related to machine learning, deep learning, computer vision, data fusion, and everything related to modeling, like surrogate modeling, but also visualization, advanced visualization. So it can be interactive visualization, but AR, VR also. So, yes. So I am just going to talk about two particular AI technologies that I think will have a lot of impact on particularly digital twins. The first one is foundation models. So for those of you who don't know what foundation models are, compared to the current machine learning techniques like early neural networks and then deep learning, foundation models are very large-scale AI models which have millions to trillions of parameters and that have been trained on extremely large amounts of data. So the burden of training this data is done upfront, but then after that, when they are used, they don't need as much training, and they are also much more accurate than the previous type of neural networks. So they have been used very successfully in computer vision, and I can imagine that, for example, they really provide, they are a way to provide different types of, taking a large amount of data and extracting the information that is essential from all of this large data, and being able to provide these new products or this new representation of the data, and they might be very useful for example, for the digital replica component of a digital twin. So the second type of AI technology that I would like to talk about is the causal AI. And so if you remember the hype curve of all the different technology, causal AI is probably still very much on the left side of the curve because it's still not a very mature field of AI. But it has a lot of promise for being able to discover relationship, cause to effect relationship, and in particular to model the impacts of one system over another. So instead of looking at statistical models that work by association, causal AI is going to discover this causation from one variable to the next. So there are a lot of different. I mean, there are various ways to implement causal AI techniques, and so this is I am not going to go through all of them, but this is, I think, an area of technology that should be very promising and that should be studied for smart cities and urban digital twin. So and especially for autonomous type decision. So then the next type of technologies are advanced technologies such as quantum and edge computing. So I am not going I am not an expert in quantum computing, and I am not going to give a class on quantum computing, but mainly the idea of quantum computing is to take advantage of the three main properties of quantum computing: superposition, interference, and entanglement, and being able to speed up the computation in an exponential fashion. So very simply, quantum computing will be able to take a problem and to look at all the solutions at the same time, and instead of looking at one solution after another, so it can speed up the computation very fast. So the quantum computing is being investigated for application in many different domains, such as finance, cybersecurity, AI, of course, supply chain and logistics, and pharmaceutical. And there are mainly two types of quantum computers: the quantum annihilers that focus on optimization, and the one that are called universal quantum computer. So for quantum annihilers, there is an operational company D-Wave, sorry. that is operational, but that mainly focuses on optimization, so that cannot solve any problems. And for universal computers, these are not yet mature, but there are some emulators that are being developed, and Yelena and Sakrat, I don't know if he's here, can talk to you about it. But they are very promising for AI. And also, of course, for digital twins. So for smart city, we can see that quantum computing could be used for example, for optimizing traffic, for the green management, for sustainable resource management, and also for urban planning, and mostly for simulation. It could, if we want to look at various types of simulation for what-if scenarios for digital twins, quantum computing could be extremely useful. And the next one is edge computing for smart cities. So we heard this morning about different types of edge computing, and again the same. This is really edge computing could be used for all the different applications that relate to IoT and the different network of sensors, being able to do some intelligent processing and intelligent decision making autonomously or semi-autonomously on the edge at the level of the sensors or between multiple sensors. So of course, for NASA, we had the little Ingenuity helicopter recently that was that had the Qualcomm Snapdragon processor on board, and that was able to perform a certain number of autonomous tasks. But there are other solutions, and this morning we heard about AI Wayson that I will have to add on my slide. But from what I understand, it's a GPU type based sensor, and there are other solutions also with GPUs. So finally, the next technology that is of interest is digital twins, of course, for smart cities. So digital twin is not a new concept. Digital twin were first invented in 2002 for product lifecycle management. It was then introduced to NASA in 2010, and then was used mainly in the aerospace and the automotive industry. Recently, in 2024, the National Academy did a study and a report in which they worked on a definition that could encompass the different fields of digital twins, and compared to the early definition, the key concept of a digital twin, where this not only the virtual information construct, which means that the mirror of a physical system by a digital system, but they also added this bidirectional interaction between the physical and the digital system, and also the capabilities of doing prediction and informed decisions. So this is a definition that encompasses all these different concepts. And we can, not only there are digital twins in different fields, but we can also imagine that all these different twins could be federated in the future. So we could have some kind of an ecosystem of digital twins that would all be communicating and that could create an entire cyber infrastructure. So in Earth System, I introduced an initiative in, I think it was in about 2019 at NASA for Earth System digital twins. And there, the interest that it was really coming at the intersection of three factors. The first one is that NASA, all the different space agencies in the world, and lately the commercial companies also, acquired tremendous amounts of data that need to be organized, distributed, and analyzed. The second factor is that because of climate change and recent extreme events, there is a demand for this data from non-traditional users. Traditionally, it was mainly scientists who were using this data, but more and more, these data are being used by decision makers, by policy makers, but also by non-traditional users like citizens in the street. And finally, because of the advance in AI and computational capabilities, it is now possible to take all of this data to create these information systems that are going to be able to analyze and process this data and distribute them to non-traditional users. So this is where digital twins come from, because these digital twins are really responding to this demand. And this is why when at NASA we derived the definition of what are Earth System digital twins, the first word that we use is information system. So very often when people think in terms of digital twins, they think only about the digital representation. But in fact, beyond the digital representation, there is this entire aspect of prediction and impact assessment. So it's really information systems that encompass this entire concept. So mainly we are defining digital twins as made of three different components. The first one is this digital representation or this digital replica, which is a snapshot of the system at the current time. So it's the current state of the system. And this is what we call the what now. Then the second component is when, based on this digital replica, based on some predictions under nominal condition, what is going to be the future state of that system, and it's what we call the what next. And then based on the digital replica, these predictions, and if we want to start doing some what-if scenario by tweaking a little bit the conditions and the variables, then we have the what-if, where what could be the potential states of the system depending on these variations in the variables and the conditions. So these are these three components that we are using for digital twins. So in urban digital twins, it is similar. So we have all these different data on the left side that are all the data that are collected for smart cities. And then there is this constant exchange of data between the physical system and all these different sensors and all these different sources of information, and the digital twin on the right. And around all this digital twin, we have all the different users that can ask different questions about the state of the smart city. So if we look at it in terms of the what now, what next, what if, the what now is the current state. So we have this bidirectional interaction. On the left, we have the physical system, and on the right, the digital replica. And this digital replica can be represented by various ways. So, for example, with a data cube, or with some GIS system, CAD system, knowledge graph. But mainly, this digital representation will include the essential variables that will be needed to respond to the questions of all the various types of users. So you have one digital representation, but you have multiple types of users. So this digital replica is updated in real time, continuously with the data. So the data can come at different times. So it might be asynchronous data, but they are, the digital replica is updated as soon as new data is coming. So the what next then is based on this digital replica and on different models. We can make some predictions. So predictions that can depend on the planning for the city, but on the local economy, on the growth of the city, on the demographic, and the demographic can change, but also can be based on climate or weather parameters. So, and then the third component, of course, is a what if. So based on the digital replica and the previous prediction, now we can make different hypotheses, and depending on the different hypotheses, we will have different outcome, and we can make an informed decision based on this what if scenarios. So, as I said, there is one digital twin, but many different users, and this is what we call personas that represent different types of users. So the users can be, of course, the first user will be decision makers and urban planners, but then it can be also emergency managers in case of a disaster or an emergency. Also local organizer trying to see, it can be a school, it can be tourism, and so on. And finally, the ordinary citizens who would like to know where their city is going, and who would like to have some information about the future of their city. So each of them will need different information, but each of them will be able to access the data. So of course we can imagine that there will be different interfaces depending on the users, because some user might need information that is very, very easy to digest, but some other ones will want to even input their own models in the digital twin to make their own predictions. So these are also different ways that it could be used. So finally, if we come back to all these different technologies, so when we will have defined all of these different technology, and the one that I have not talked about was cybersecurity also, that is a very important component of this type of systems. But when we put all of these different technologies together, we can build a cyber infrastructure or a metaverse of the smart city that will combine not only the digital twins of the cities, of the smart cities, but also Earth system digital twins and human digital twins, and all of these could be even represented with knowledge graphs or knowledge domains and ontologies. And then between these ontologies, they will be able to be federated, because the information from one digital twin might be able to be used by another one. And it could be used not only for decision making, but we can also imagine that it also could be used for education, for future students. So this is really in the future, but this is where the evolution of digital twin could go. And I think this was my last slide. Yep.
Thank you so much. Jacqueline, great job. Super exciting to have you here and honoring us with your presence. Could you talk about how you see, we had a chance to talk a little bit about what's going on to make a digital twin testbed to help connect like government, academia, private sector, things like NASA. What do you think is the best way to help land the plane on some of these systems, like the first 3 baby steps to start moving in this direction so that state and local government can start to kind of interoperate and take advantage of these larger sort of NASA digital twin systems?
Okay, yes, this is a big question, but for a system digital twin, we designed a system architecture of what would be a digital twin. So we didn't try to mandate what should be the architecture of the digital twin, but what we did is that we defined what should be the main components of a digital twin, and with the idea that eventually digital twin could be even a plug and play type system where the users or the developers could bring their own components and plug into this architecture. So one thing that is important in this case is not to define the architecture as a whole, but to define the interoperability standard that will be needed for all of these digital twins to communicate. So this interoperability, there are a lot of papers about interoperability. It can be defined at different levels, from the semantic level to the legal level to the operational level. But we can define it either at the component of the digital twin, but we can also define this interoperability at the level of the information that comes out of the digital twins, and that can be used by another digital twin. So these digital twins could be federated at the level of the information, or they could be interoperated with the models, for example.
Yeah, I just want to echo a fantastic talk. One of the questions I have about interoperability is how do data ownership issues get woven into the interoperability between different organizations or institutions, things of that nature? Because everyone's getting more and more possessive with their data.
Yeah, this is a good question. In fact, I am part right now of an IEEE group that is looking at this kind of issues, and that we are in the process of writing a white paper that will define some kind of guidance about these kind of things. But there are a lot of questions that still remain at the level, as you say, of data ownership and IP, and also the sustainability of these digital twins, because when we start federating them, who is in charge of sustaining them, and so this is the kind of thing that are still in progress. Yeah. Okay, thank you. Oh, thank you.
Sorry, just one more question. Thank you, a wonderful talk. Just a quick question. You mentioned in your talk about the definition of a digital twin, about a bi-directional interaction, and about how it would take in data from the true environment and then inform decisions. And I was wondering, why just inform decisions? Why not like actuators, such as deciding to regulate water supply or power grid, or deciding to close or open lanes on a highway, or even agents that would go out into the environment and start interacting? Why is it just in decision making, or do you see that the bidirectional could really expand even beyond that definition?
Yes, I talked about decision making mainly because I was focusing on smart cities and where it is right now. But I agree completely that it can go into actuators, and in fact it could be like you say, an agent-based system accessing a digital twin. It doesn't have to be a human also. I mean, it could be completely autonomous too. Yeah, I agree.
AI-based decision-making and everything that goes with it. So for instance, let's say there's a fire in some part of the city, and we do not receive any call or any type of information, specific information about it, but we sense it. Before the abnormality happens, I'm not sure, we sense that there is some type of abnormality, the smoke is coming out, and we deploy all of our resources to that end of the city, where in fact, the problem or the actual fire was going on the other side of the city, which is basically cyber vulnerability, right? Cyber attacking. So how do we prevent that, especially when we are making decisions in the real time, when we are using the data at this second and not going back to the historical data? So basically, how can we trust the decision making of the AI when we know that if we train it well enough, it's going to give us accurate data? So it's going to prove itself that it's given you an accurate data where in fact the data is flawed. So could you comment on it a little bit?
Thank you for the excellent question. By the way, it's nice to see you again. Several years ago, you actually gave a virtual seminar at UF, where I previously worked. So yes, I definitely recognize you. So quick question. First, I have to be honest. I haven't yet given much thought, to the reliability of the data, the signal and so on. But it does remind me of something I was talking about earlier. It seems to me that it's highly non-trivial to turn signal into real decision making, right? So think about the occupancy level at the ER, right? At what level you initiate something? 75% or 90%, right? Or the wastewater scenario. At what level you actually initiate some precautionary measures, right? So if you act too early, you have the risk of wasting resources. If you act too late, it may cost lives, as the situation you just depict. So to be honest, I don't have a very specific answer to that, but I do feel this is very important. How and when to turn the signal into actions. Thank you.
Wonderful.
Maybe I can add a little bit to that.
Please.
Yeah, because that's actually also a concern in our company as well. So what we actually do is that whenever we give an answer, like in the clinician decision support, we always cite the source where this is coming from. So that could make the answer from whatever the model more trustworthy, reliable, so that human can more easily to verify rather than out of box. So that's one thing.
It's wonderful. Now, with regards to health and wellness, and with regards to smart cities, what keeps you awake at night? And think of that as a next step question. What happens next? What worries you the most with regards to health and wellness as well as smart cities? If you could just comment on it quickly, and we would probably begin to wrap this up.
I guess
wanna hear from all of you.
I'll start with that real quick. I mean, obviously, I have a passion for what we do with water, but this, I think, has a big implication with the discussions that are going on with the resource requirements for AI. And a part of that is cooling, and the cooling comes with water. So, there's been conversations happening throughout the country where some places are experiencing issues because they'll put in this data center and all of a sudden there's a lack of that basic resource for the residents in the area. So, when we're looking at building smart, we want to make sure that there's that delicate balance that, okay, we're employing these tools and these technologies to help make the, life better, to improve the quality of life. But we have to do that with a real focus on balance to make sure that we're not subtracting from one area just to add to the other.
That's powerful. Okay, I want to hear from all of you. Yes, Ed, if you want to go
Dean,
on.
when it comes to health and wellness, I become very selfish. And I cannot escape the adding to that health, safety, and wellness. And for the past 4 months, I've become acutely sensitive to our vulnerabilities, not as a country, but also as a community, and being able to be self-sufficient and not rely on foreign powers for our health and wellness. So making sure that we have the systems in place locally so that we can continue to operate without having someone from outside of our borders pull the plug and hurt us.
Wow, very good. Thank you. Yes, Helena.
Yeah, I was reflecting as well. I mean, in addition to my area, which is environmental, the whole question about AI and artificial intelligence, and as I was reflecting on it, smart cities need smart people. And in terms of, in this world of artificial intelligence and where we as faculty are to impart and help students grow, it's becoming very challenging to really know, are they being educated? What are they providing us back? And how do we evaluate it so that we know that we're imparting knowledge, that the students are not, making things, cutting corners and giving us materials. An example I have is I'm teaching a class. I have over 20 students, and they were to provide me with a report, a 2-page report. 3/4 of the reports were the same. They were very similar, and I was like, this is not right. So how do we make sure that our smart cities have smart people? And I think it's the underpinnings is the education and making sure that when we teach, we're evaluating the students that they really are truly learning. And I think that's a huge challenge. Thank you.
Thank you for sharing that. Yes, you.
Thank you. So I will be brief. I think a smart city ought to be human-centered. Okay, human ought to be in the center of everything. I just want to briefly share one example. Several days ago, in the apartment building I live, I saw several drones performing the high-rise cleaning instead of people. I didn't know people can be so creative using drones to do this type of things. So I do believe we can be more creative in terms of how to make a better use of the technologies, the data, to make our lives better and safer.
Okay. Yes, please.
Yeah, I will also add one point that's probably not keep me awake, but keep many people awake is whether one day AI will take their jobs, right? So I actually get this question a lot from my friends, and they worried about the future like that. So what worried about me is people too slow to adapt to AI tools. Like the speakers have mentioned that AI is a great tool to make our work more efficient. It will replace some jobs, of course, but not just replace totally. So let's say the constructors, now they can use AI to estimate. So their job is more like verify. We still need to verify whether the estimation is correct or not. So they are not totally replaced, but it's important for them to adapt to how to use AI tools. And that's not like easy for everybody. And we kind of lack of that kind of training as well. So I think that's probably a worry for me.
Okay, how about a round of applause for our distinguished panelists? Thank you so much, and thank you to our audience. And that's the end of the session. Thank you. Okay, absolutely.
It's getting to the end of our conference today, so we have our final keynote speaker, Professor Dan Frankopaul. Dr. Francopour is the inaugural Fazla Khan Endowed Chair of Structural Engineering and Architecture Emeritus at Lehigh University. Before Lehigh, he was a professor of civil engineering at the University of Colorado Boulder. He is recognized as a leader in the field of life cycle engineering of civil and marine structures. He's also the founding president of both the International Association for Bridge Maintenance and Safety and the International Association for Life Cycle Civil Engineering. He's a member of the National Academy of Engineering. He's also a foreign member of the Canadian and Mexican Academies of Engineering. There are so many academies of engineering here. And he's also a distinguished member of ASCE and founder and editor-in-chief of the Structural and Infrastructure Engineering. In 2023, ASCE established the Dan Francopour Medal for Life Cycle Engineering of Civil Structures. So he's a legend in civil engineering. So we are honored to have you.
Thank you, Mekoi. I'm indeed very pleased to be here. It's the first time that I participate at this conference. You hear me well? Yes. And I have about, 6 minutes? I want to stress out that this talk will be on the resilience and not only on resilience but also sustainability. I think these things are related. And I'll talk about resilience sustainability of civil engineering infrastructure. Generally, when we talk about a city, or if you talk about a structure or a group of cities, we have to look at not at a single structure, but of a group of structures and a network of structures. And you can talk about a city, you can talk even about a state or even a country. We have things like corrosion, fatigue, material degradation. You have all these systems under natural and man-made hazards. And you have to look how to inspect, how to monitor, how to maintain, how to replace these systems. So you have to make decisions. You know, American Society of Civil Engineering is one of the largest societies with about 150,000 members. Every 4 years issue a report card about infrastructure in general. And they give a grade, which is not a good grade for our students, and for us was a D+, and now is C. For bridge was C+, and now is C. And what is important is that the concept of life cycle is a very important thing that AEC recognized for about 15 years. And things like life cycle cost, like optimization, are new things, and they have to be looked together. So smart cities, we have to look at how to optimize, how to make a better life, how to minimize the cost, and how to make the best performance of our systems. We are threatened by earthquake, not so much in Florida, but you have hurricane, floods, and fires. United Nations Office for Disaster Risk Reduction reported that in 2011, the natural disaster resulted in about $360 billion of direct losses. Now it's more than 1 trillion. Population growth, very significant. In 1970, we have about 3.7 billion. Now there are more than 8 billion. So population growth is also an important factor that you have to look. And we talk about smart city, what will be the best population for a city. How to mitigate hazard, how to look at the resilience and sustainability of system is an important thing. Over 50% of the US population lives within 50 miles of the coast. We are now in Miami, so we are very close to the coast. And you can see this growing population in coastal region is quite impressive. Floods are almost everywhere, and you can see due to climate, these floods are increasing a lot. If I take just one city, you can see that from 1950 to 1959, 69. So for 20 years, we're about 5. From 1970 to 1981, about 15. In 1990 to 2009, more than 20. In 5 years only, 2010 to 2015, were 35. So really, hazards are with us now. We have natural and man-made hazards. We have aging and deterioration processes, population growth. And now there are some concepts. The concept of reliability, safety. Everybody talk about safety. Now we talk about risk. Risk is more comprehensive than safety. So we can have similar structures with the same safety, but the risk could be very different. Because risk involves cost also, sustainability and resilience. About 30 years ago, I published this paper with some of my students, University of Colorado in Boulder, in which you have a performance level. This performance level is deteriorating in time. You don't know exactly when, what is initial performance. You don't know exactly when deterioration will begin. You don't know exactly what is the life and what is the deterioration rate. So you can have uncertainty. You have to deal with uncertainty. It's not possible to have smart cities without dealing with uncertainty. Let's try to minimize these uncertainties. So if you don't do anything, the life is quite short. If you do something, you have to pay. So how much you have to pay is also your choice. You can extend the life, you can see, or you can do preventive maintenance, or you can do an essential maintenance to extend more the life, but you have to pay more. So is it worth to extend the life for 5 years, for 10 years, for 15 years, or is better to replace the system? You can see the two requirements: performance deteriorating in time. If you don't do anything, you have service life without maintenance, service life with preventive maintenance, service life with preventive and essential maintenance. All the time you have uncertainty, but if you do something, you have to pay. So performance and cost are the two objectives, and you want to maximize the performance and you want to minimize the cost. How to deal with this? Uncertainties, as I mentioned, are important. You have performance indicators. Generally, until 10 years ago, people talk about reliability, redundancy, and after you have high consequences, like accidents in Japan or in other places with nuclear power plants. So high consequences. So risk is combining the effect of probability and consequence of failure. You have to look at risk. These are things that I already mentioned. You can have probability of failure, which is safety, basically, and the other part is risk. If I have a building or a group of buildings in New York City affected by hurricanes, and if I have the same group of buildings somewhere in a location that is not so important, and the safety could be the same, but the risk is much larger in New York City because it affects a lot of people. So you have to talk about risk, which include the safety and the consequences of failure. Without talking about risk, comparing only safety is not enough. So people talk about resilience, some people talk about sustainability, and you don't make too much difference between these two. You can have resilience in buildings or in a city, and sustainability is more than the resilience, because you can have resilient systems that are not aesthetic, that are not economically good to maintain them. Sustainability is for an entire generation. So sustainability includes resilience. You can have resilient structures that are not sustainable, but you cannot have sustainable structures that are not resilient. So you can do, when you maintain a system, you can see you can do some essential maintenance activities, you can extend the life, or you can do preventive maintenance and you can extend the life. The problem is cost. How much you can extend, how much you have to pay. People are working in mechanical models, in finite element analysis, in structural health monitoring data, and you can use the so-called Bayesian updating for better estimation. So it's important to estimate better, to minimize uncertainty as much as you can. And these are the two indicators that I mentioned, performance and cost. You can see every time you have an event like an earthquake, you can don't do too much about this. The performance is reducing, but sometimes you have to repair it. When you repair it, you improve the performance, but you have to pay. So repair cost and performance profile. And you can see that is a big difference between the initial cost and the total cost. About 20 years ago, in structural engineering generally, when you make a bid, and one guy is given 5 million and the other guy says 7 million, you just choose generally the one which is low cost. But you don't look at the maintaining the system for a period of time. Now it's required to look at the life cycle cost, means how you can maintain the system, how you can repair the system for a period of time, say 50 years, 70 years, 75 years for bridges in other countries, 125 years. So this thing, cost and performance, and they have to be optimized. So you have to minimize the cost and maximize the performance. And we are lucky to begin this type of computer models and things that we develop at the University of Colorado Boulder, and after we work at Lehigh University, and one of the people here, Mi-Hui Cheng, also contributed to these things. So, as I mentioned, sustainability involves economic part, involves environmental part, and the social part. So we have to talk about sustainability, and this includes, of course, resilience. So we develop different type of modules, going from reliability, from risk and resilience and sustainability, and we have a computational platform in which all these metrics are evaluated. And sustainability is perhaps the only equation I give it here, but I think is important. You have to look at annual probability of occurrence of a hazard. You have to look at the conditional probability of a damaged state given the hazard. You have to look at conditional consequence given damage state at the time, and you have to integrate this over all the damage state and all over the hazard. This could be a good model for a system, for a city, for any important investment that you want to do. Just to give you an example here in which you look at the system individually or you look at the systems that are connected. For example, it's a group of bridges in near Los Angeles area in which we look at what will happen if I have to repair each bridge by itself, or what you have if I have to look at how this network communicate, and the important bridge have to be repaired first, and another one perhaps is not so important, we can repair later. So is very much involvement in decision-making processes and the difference between individual system and interaction with other systems. So this is a computational platform that I mentioned, and in which this was implemented, and we have it in final form at Lehigh University, in which you can have decision about optimal lifecycle management of systems or group of systems. We include lifecycle optimization, we include sustainability and resilience. We did this not only for civil structures, but for marine structures. I was lucky to have a lot of contracts from Office of Naval Research. Concept of lifetime resilience. I think it's important to mention that people look at resilience at one point in time. It's not good because you have different hazards during the life of a system. You have to look at resilience at different points in time and accumulate all of them. So you can see how its performance deteriorating, and after you have a path in which the performance is going below the target level, so you have to have a recovery action, and you have to know how long you have to wait for doing this recovery, how you can do it, and so on. Resilience has different dimensions: technical, organizational, social, and economic. You have some properties: rapidity, redundancy, resourcefulness, and lower consequences, faster recovery, more reliability. These are the things that we have to look. So if a hazard will occur sometime, you have to have the functionality dropping a lot, and after you have to have a path for recovery. And you can define resilience by the area that is under this curve divided by the total area of this time of recovery. With this in mind, we can look also at uncertainties, and you have uncertainties in functionality, and you have uncertainty of how much the functionality was reduced, how long you have to wait for doing actions, and also how we can recover at what time and what will be the cost for this recovery. This is a big difference between sustainability and resilience. You can see here, this was a published paper about 12 years ago, in which you have a community infrastructure in its life cycle, and you can see the difference between resilience and sustainability. Resilience occurs only at a certain point in time when you have hazards that will affect the system. But sustainability has to be in all the period of time. You can see the lower part is sustainability, the upper part is resilience. Now, I talk about optimization and what you have to optimize. People say, okay, I want to optimize. What to optimize? Some people will say, I want to maximize the resilience index. Other people say, I want to minimize the total cost of interventions, or minimize the total recovery time. Rapidity is very important. Or minimize the time required to reach a target functionality level. So, any constraints, many constraints, la total cost, deliver the minimum functionality levels, maximum number of simultaneous intervention associated with self-fulness, additional constraints on the rehabilitation parameters. And now we talk about lifetime resilience. As I mentioned, lifetime resilience means you have a performance level is deteriorating, and after you have to repair. You repair until the level that is structure deteriorated, which is the first one and second one of these graphs, or you repair at the higher level, which is the initial performance. So you can define the lifetime resilience using the formula above. Now, I work also with a colleague from Japan, Professor Akiyama, in which you look at different levels and you took the reliability, risk, and resilience. He's a professor at Waseda University, and you can see the difference between reliability, risk, and resilience. And if you have, we look at coastal regions, could be, I think, close to San Francisco area or even to Miami. You don't have still earthquakes. But you have multiple hazards. Here you look at seismic hazard, tsunami hazard, chloride hazard, which is contamination through corrosion. And you have the problem of migration of chlorides from the sea to the systems. In addition, you have global warming, and you have a lot of other things that happen to deteriorate here in a bridge network. And you have to look at reliability, risk, resilience. Another difficult problem is disaster waste management. This happens a lot in Japan, and how to deal with waste management. So what would be the challenges and mission to our resilience infrastructure systems? There are basically two missions. One is to look at the resilience of infrastructure under multiple hazards. The other mission is to life cycle management of the agile infrastructure, and here you have the points that are important to look. Community resilience is an important topic, and we have to mention that the United States funded Center for Community Resilience in Colorado, in Fort Collins, and they developed during the past 10 years a lot of good things, so I want to report what they did and also to summarize some work. Generally, if you look at the Community Resilience Initiative, there are many initiatives. One are international initiative, national initiative, regional initiative, and local initiative. For the international initiative, you have the the United Nations Office of Disaster Risk Reduction, and for in 2013, in the wake of Hurricane Katrina, they did this 100 Resilient Cities initiative. And you know about the national initiative. I don't have to mention them, but I want to mention the NIST funded this project for community resilience in Colorado, at University of Colorado at Fort Collins. Regional initiative, there are some. For example, this initiative, which is Pacific Northwest Economic Region, including all these parts in the northwest of the United States and Canada. And also local initiatives. For example, this one that is a baseline resilience indicator for communities, educated different counties and all these type of initiatives that were done. Resilience frameworks, you know, this is a formula that I already mentioned, with the components of resilience, quantitative attributes, and how to quantify resilience. And is an important framework, this, the people's models, in which you look at the 7 dimensions involving population, environment, organized government services, physical infrastructure, lifestyle and community competence, economic development, and social cultural capital. There are also different steps to process community resilience planning. This chart that NIST provided, in which you look at the set of performance goals, you evaluate the infrastructure, you establish design criteria, you conduct risk assessment, set the recovery metrics, and to achieve resilience finally. There are advanced quantitative models. One was proposed by Professor Ellen Good, that he is part of this effort on resilience at Fort Collins. And we have the physical, social, and economic systems that are important. And these systems are also interdependent. So it's important to look at the smart cities, whatever, looking always at the interdependency of different events. And how are the foundation of these models, what is the vulnerability quantification, how we can find complex network interaction and probabilistic method in recovery. For physical infrastructure systems, we talk here about hospitals, building and so on. We have hospitals and acute care facilities, and we have a framework and models. There are some papers on this field. And for a group of buildings, also there are different, I put here different authors and papers addressing this topic. There are also, beyond hospitals, you look at socioeconomic links. Beyond earthquake, there are different studies with flood, hurricane, and social and economic functions. Now, infrastructure systems, we can talk a lot about different type of infrastructure systems. These are focusing here on power systems, and this focus on post-earthquake restoration simulation. Of course, if you have damage of these systems, this will involve many other facilities that cannot work. Lifeline systems, water networks, a very important field. Gas systems, transportation systems, and how to define for social system measuring of resilience. There are different measurement methodologies and conceptual frameworks. Again, for social system defining and measuring resilience, we have empirical studies and some critical gaps, and these are some papers relevant to this field. And of course, economic systems, IO models, so input-output models, computational generation, equilibrium models, dynamic spatial models. What I want to mention is that to take into consideration this interdependence is crucial in all the studies. You can study a thing that is extremely well and do proof of these systems, like they did a big errors in Japan, especially, they restored many bridges for earthquake. So basically, bridges could resist to earthquake of magnitude 9 without having too much damage. But many bridges were located near the water, and basically when tsunami came, all the bridges were out. So without looking at the dependency between events, you can make big errors. Other bridges in other countries were damaged. Also, there were proof for seismicity, but were damaged by collapse due to slope stabilities and so on. So interdependency is a very important topic, and look at the system of systems, not just one system. Of course, water could be by itself a system, but you have interaction with power, with wastewater, with natural gas transportation, and so on. So system level functionality and community resilience are very important topics to look. And some research needs to develop system of systems, to validate metrics and models to advance decision tools. These are some recent books that one of my students and I wrote about. This one is on bridges, the other on marine structures, and the combination of both for these topics. With this, I have to thank you very much for your attention, and I hope you have still time.
Professor Frangopol, thank you for being here. We really appreciate the knowledge you shared. I had a simpler question, actually, because you refer more complex, right? Because it's fundamental in a sense that sustainability and resilience both have been used in your presentation simultaneously. Could you elaborate where they converge and where they differ in this space?
What I mentioned, these two concepts are very important, resilience and sustainability. Sustainability generally is a thing that you look for our generation, how to transmit it to the other generation. Resilience is generally in front of hazards. You have a resilient structure that will not have so much damage, and or if it has damage, you can repair it very quickly. So resilience is for some point in time. Sustainability is for a longer period of time. You can have resilient structures that are not sustainable. You can have a structure that is very proof safe, but is not aesthetic, is not economic. People want to get rid of it. So it means a resilient structure is not always sustainable. Yes? So, but always a sustainable structure has to be resilient. So this is what I think about.
Professor, thank you so much. This was really enlightening. I was curious about the connection that you established between and among systems. So if an earthquake happens, an earthquake event happens in the West Coast, for example, and simultaneously or perhaps a few months later, there is a wildfire event. How do we have enough data to establish the connection between these two events in order not to ignore whatever causality one might assign?
Some events are statistically independent. For example, you have an earthquake, and after 10 years you have a fire. It has nothing to do with the earthquake that's 10 years before.
That's right.
Some events are very, very dependent. For example, you have earthquake and you have shortage in water, and you have shortage in power system, and you have everything like this. So in this system, you have to have all this interdependency taken into account.
Okay.
You have to make difference between independent, statistically independent events, and events that are related.
Okay. I see.
But for some time, could be in time that, for example, a slope stability could occur because it was an earthquake 3 years before, and you have a rain, and the slope stability was also affected by both the earthquake and by the rain. So you have to look at this in this way. Yeah.
That's wonderful. Thank you.
as we come to the end of today's conference, I would like to take a moment to reflect on today's fantastic event. So smart cities we have seen that smart cities have evolved with new technology. So we've seen new sensors today, new hardware and software, and also new services. We've seen that smart cities has make our lives healthier, make our infrastructure stronger, and delivering new services. But we have also seen many challenges. So today, many panelists mentioned the adoption challenges, also the privacy issues that hinder the adoption. So that's why our conference today is trying to bring together researchers, industries, and governments. We are going to work together to try to make the technologies to have real impacts. And finally, I would like to thank all the keynote speakers, panelists for their insightful talks and discussions. And I would also like to acknowledge our fantastic staff, Eve, Francis, Saab, and Justin. Without them, we would not have this conference today. And finally, I will encourage everyone to go to there is a nice reception out there. And yeah, that's all. Thank you for joining us today.